will be torn down into 3 sections and then returned by helicopter to the vehicle assembly building, and then the experimenters and researchers will then begin to take a look at the results. So that gives you sort of a quick rundown on the payload and what we anticipate to happen this morning.
This vehicle, those of you that haven't seen it before, gets off the rail very fast. It's not quite like watching a liquid, one of the NASA launches that sort of climb out reasonably slowly. This one gets off like a missile, because that's what the first stage basically is. You'll see the first stage burn out, the order of 6 seconds. Then you'll see a coast phase, and then you'll see the second stage ignite after we have reached the right dynamic pressures to do that. The sustainer motor, our second stage, is a fairly long burn time, so you'll see that climb out. As the plume of the vehicle climbs out through any wind shears, don't think there are too many today, you'll see the plume sort of scatter around a little bit. That's not the vehicle maneuvering like that. The vehicle hopefully is going straight down range. That's just the plume being hashed about. Wendy Beatty, who's doing the count for us, she will give us the plus count, and at T plus 12 seconds, she will announce second stage ignition. That's at an altitude of 3.75 miles. And then there'll be a plus count at T plus 18 that we'll hear. That means the end of the S-19 boost guidance system. That occurs at about 6 miles altitude. T plus 44 is the next count. That's the end of the second stage ignition, second stage burn. And that's about 30 miles altitude. T plus 52, we have the payload despin. That means the vehicle that was spinning up due to the fin cantangle set in to give us a spin stabilized vehicle. We have what we call a yo-yo despin, which is simply some weights that come out on long wires, much like a ice skater puts her arms out to stop the spin. When she's spinning on the ice, it changes the moment of inertia in technical terms, and then as she puts her arms down, she'll spin up. But we will put this despin, yo-yo despin system out, and that essentially takes all the spin rate out of the vehicle to make us ready to enter the microgravity condition for the experiments. We'll get a payload separation at T plus 58. That's at 48 nautical miles, or excuse me, not nautical miles, miles. T plus 74, we have the beginning of the microgravity period. And at T plus 290 seconds, we have apogee, which is actually 198 miles for this mission, but close enough to 200 miles altitude. T plus 506 seconds, the end of microgravity. At 68 miles, that's as we arc over. T plus 622 seconds, the main chute will deploy. We'll get an indication of that. You're not going to see that today. And that's at 3 miles altitude. And then T plus 878 seconds, we will have a payload landing 50 nautical miles downrange. So it's about a 15-minute flight. It's 878 seconds. So I'll keep quiet here now. We're close to the launch condition, I think.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Rocket away. +2, +3, +4, +5, +6, +7, +8, 9, 10, 11, 12. We should have second stage ignition at 3.75 miles altitude.
should be able to see the
+35.
stage burn.
+85 seconds. +90 seconds.
The Consortium for Materials Development in Space at the University of Alabama in Huntsville was formed in September of 1985 when the university received a NASA grant from the Office of Commercial Programs. The intent of the consortium is to promote commercial activities in space and to enhance the technological position of the United States for foreign trade. We are intending to run experiments, and we are performing experiments in the low gravity of space so that we can learn things about materials, make new materials, learn things about processes that we can't learn on Earth where they are masked by Earth's gravitational pull. The nice part about a sounding rocket like this is that it can be done approximately every 6 months or so. Our first launch in March of 1989, Consort 1, was a successful launch in which all of the experiments worked and worked very well. That payload was built entirely by UAH and integrated by McDonald Douglas Space Systems Division in Huntsville, Alabama. On Consort 3 then is experiments not only from the UAH Consortium for Materials Development in Space, but also from 3 other NASA Centers for the Commercial Development of Space, from Battelle in Columbus, Ohio, from Penn State University, and from the University of Colorado. We also can change experiments very close to launch time. As opposed to if you're flying on a man-rated vehicle like the shuttle, there are a considerable amount of documentation that you have to go through. Safety documentation to assure the launch people and to assure the astronauts that we are not in any way compromising their health and well-being. The foam formation experiment is looking at the $1 billion a year home insulation market as one application. It's also looking at building structures on the moon for going in a lunar Mars types of missions. The foam formation in this particular experiment will have aluminum particles in it so that we can see what the effect of aluminum is on some of the acoustical properties of the material. The reason we want to study the foams are that if we can make a small amount of improvement in the way that foams are currently built, with there being such a large market for it, any small improvement can have a large potential savings in energy and also in production costs.
Our interest in the project starts from some general observations that have been made for every cell, tissue, human, animal that's gone into space. That is, that there are a series of subtle changes in physiology that have been observed, maybe roughly categorized as changes in cell secretion or changes in hormone response. While these might be quite unimportant, one really doesn't know the importance of these over some long-term experience in the microgravity arena. The other intriguing part is these problems that are seen in microgravity are also very clearly related, in our minds at least, to general unsolved disease states on Earth, such as cystic fibrosis, diabetes, and so forth. So the question for us became one of, can we get double money out of our experiments here, where we can use microgravity as a test tube in order to learn something about these important diseases? In order to do that, we have to sample a microgravity experience, and we have to learn something then about the behavior of cells in this situation. This is why we've constructed what we call the Penn State Bio Module, which starts from a modular set of about 8 experiments the size of an eraser. And in this, we can put solutions in the various sidearms and cells and tissues of interest in the main chamber. This becomes the fundamental unit that we work with. These then can be assembled according to the geometry demanded by the payload onto a base plate. And here we see a base plate with our little computer, auxiliary electronics put underneath, and placed for 4 separate biomodules, and this is what we'll be flying in the Consort 3 flight. We picked the chameleon skin and tadpole skin problem. Basically, everyone's seen the color change that occurs in chameleons, They may have seen the spot changes that occur in tadpoles. These color changes, although they are very similar in overall respects to much more complex processes involved in humans. Now, the value of these systems are the tissues are very robust, they're easy for us to prepare, and we can do meaningful experiments in this particular environment. So what we're setting up here is to test proof of principle. The question we're trying to ask then is, someplace over 6.5 billion years of evolution, cells have learned to handle gravity as a settling force within them, and I have made use of that, we believe, for other processes that are involved. We're trying to ask simple questions like, when a chameleonkin goes into space, and if it's challenged with an appropriate hormone, does it change color in a manner that one would predict? This is the spirit that we're going to follow.
As the payload integrators for Consort 3, McDonald Douglas has a number of responsibilities. We've worked on this particular payload for 4 months, most of that in Huntsville, beginning with the understanding and the implementation of the experiment package requirements and the build-up and checkout and integrated testing of each of the experiments in the payload. There are 12 experiments in there and several other pieces of supporting hardware, accelerometers, power supplies, power distribution systems, computers, accelerometers. All these things have to work together 100% to conduct the mission, and our job is to see that that happens.
Same view, Pete. Well, over it is. Good job.
This is nicer than last time, I think.
No, for sure.
Right.
Well, I guess Pete's probably kept you all up to speed on what's happened here. I don't know exactly. We had a couple small problems down there. Of course, we had a 10-minute hold at the end, which was a range problem. The radar went down, and we finally got an alternate radar online and went ahead. We also had a gyro problem again, and we had a noise signal on our pitch gyro, and we scratched our head pretty hard there for a while whether we should scrub or not, but Mark ended up talking to the factory guys, and we consulted with NASA and finally concluded that we could fly safely, and did. So all in all, it looks like it was a good flight. We don't know of any anomalies during flight at this point. The vehicle landed in the sand up there, should be in excellent shape. We believe that the PIs got all of the data that they were looking for. I think there was indications one experiment may have malfunctioned a little bit, but at least everything flew exactly the way it was supposed to fly. So at this point, we're very happy.
Good.
David Hanna's rocket company has done it one more time.
Put us together. Thank you.
They have telemetry on a number of their experiments. Some of them they don't get the data on until they land, but there are some functions that show up on the telemetry. I believe this was the foam experiment, but I'd rather not speak to that. Actually, Fran Wessling or Dr. Lundquist or one of their people should discuss that, because we're really not qualified to speak on their behalf on that.
Did all the other teams go okay? The other teams?
As far as we know, everything went just fine. Yeah, the attitude stayed. We only had 3 thrusters fired during the whole zero gravity period, so they should have got some excellent zero gravity, which is the purpose of the flight, of course. Pardon? What's next? Well, we're working on a whole variety of launches. We have a crew back in Houston now working on a proposal for NASA, which is, these are orbital flights, 10 orbitals. There's a Air Force proposal coming out here within the month for another 40 flights. We're working on some, these are all orbital also. We're working on a number of programs that involve suborbital, such as you saw here today. So we've got a lot of stuff out there ahead of us that we're working on, and we're very confident that we're going to end up doing. we got more proposals than we can handle here between new and launches, but that's a nice problem to have. We don't object to that at all.
Does this today's flight put you in a good position to get one of those proposals?
Well, yeah, today's flight certainly. Anytime you have a success, it's obviously helpful. I guess if you fail, it's prone to give you more negative than a success is to give you positive, unfortunately. But it was obviously a big help to us. We think everybody in the industry actually to have a success. It doesn't help anybody in this industry for anybody to fail. So we're happy when we see anybody succeed, and of course, especially when we do. But
you had some tense moments on this one, as you said, a little bit of a radar problem and then the gyro again. Were there some tense moments emotionally as you guys got into this, knowing that you really needed it to fly?
well, we don't get too tense. We've been involved in a lot of them here. We had guys flying on them. As long as you're unmanned, the worst that can happen, you know, is not too bad. But no, we were not tense, but we had some serious discussions there about whether we should or shouldn't until we got more data. We were a little bit concerned there. We might in fact have to scrub, and if we did, we were looking at anywhere from 3 to 6 days of slippage. So we were very happy we didn't have to do that. But on the other hand, we weren't about to do anything dumb. We wanted to be very confident that it was going to go good before we went into that final 3 minutes of the count.
Which last time was kind of an anomaly. I mean, as far as that little capacitor falling loose, must have been very frustrating. And then at this point, you really needed this one to go.
Well, you're right. The last one was a kind of a weird thing. I guess in this business, you know, you apply a lot of skill and cunning is the right choice of words, and do the best you can. But there's always that 1% or 2 out there that's pure luck. And once in a while you have bad luck, and that happens to everybody in the business. And this was just a case where I think everybody had done everything you could reasonably expect them to do. The same system had flown a number of times in exactly that configuration, and we just happened to get bit by it. So it was an accident there waiting to hit somebody, and we just were unfortunate. The other frustrating part of that one, of course, is we were only half a second away from a successful flight. If we'd have kept flying 1.5 seconds more in the last one, we'd have had a good flight just like this one. So, you know, you're just that close between success and failure in this business. Yes, it is. Yeah, the hardware we use, the guidance package and the recovery system are reused. They're refurbished at the factory, and this system we flew today, I believe, is our 3rd flight we've flown that hardware. So no, I think we're not concerned about wearing things out, if that's essentially your question, although that's always possible. But no, we send it back to the factory, get it refurbished and re-verified, and it's basically comes out as new equipment from a functional point of view.
Does that happen after every flight?
Yes, it does. You bet. Yeah.
How far on target was the payload as far as its landing site?
Actually, we only missed about 2 miles. Where's Mark? Mark Daniels has got the exact number, but I believe we were targeted for 52 miles, and we landed at about 54. So this is well within the limits you'd expect. Mark is running continual wind checks and launcher settings throughout the count, and he gave him the last one. Mark, you want to come over a second? There was our program manager, Mark Daniels, who's the guy that really made this work. And they were wondering how we did on the impact relative predictions.
Well, we were right on the money with our impact predictions. We were predicting about 50 miles north of here and 6 miles west, and we impacted 54 north and 11 west. So that's about as close as you can get to being on the money. That's correct, 54 miles north of the launcher. So we were about as happy as I think you can get with everything, all the systems and the performance today.
It's a signal coming through on the TM, electronic noise, the wiper arm that goes against the gyro itself. We think there was some contamination there on that, and so it was interrupting the electrical signal, and this would have given you feedback into the servos, which would represent itself as a chatter in the control system. We concluded that even if it had in fact happened in flight, it probably would not have reacted into the vehicle. We'd had enough filtering in the electronic system plus dynamic damping in the vehicle itself that it would have not been a problem, but as you can imagine, we're pretty conservative at this point, and we weren't going to gamble until we convinced ourselves that it was really not a problem.
Even though this isn't the same type of flight as Conestoga would be, do you feel that today's flight gives you more momentum toward winning one of those orbital flight contracts?
Yeah, the question about how this relates to the orbital flight actually takes the same kind of a team. Exactly. We have different players, but the difference between an orbital flight and this one from the mission preparation and the launch is very, very similar. There's not a lot of difference, really. Almost no more people involved, as a matter of fact. The only difference is instead of going up and coming down, we go to the same altitude and keep going. And in fact, most orbital flights don't even go that high. You flatten out and you just use the energy to accelerate the orbital velocity.
If you win one of those contracts, when would your earliest orbital flight be?
The NASA contracts are set for a mid-93 first launch. The Air Force is fall of 92, and there are a couple other programs that could be in the mid to late 92 time frame. Probably nothing in 91.
How do you feel right now, I guess, as far as your chances to win one of those contracts and get going on that side of the business?
Well, we feel very good about it. We've felt since day one that we have an excellent orbital launch system. We believe it's the best one the country's got. Of course, we're a little prejudiced, we'll admit, but it's based on highly reliable components, and we are able to insure it. The insurance companies have looked at it and set our premiums, and we've got about as low a premium as anybody in the country. So we think that's a vote of confidence in our system. So we think we got an outstanding system there. We just hope we have the opportunity to go use it. I think Dr. Lundquist from the University of Alabama is here, and there were some earlier questions about the payload, and he's the guy to talk to those. So does anybody have anything else on the launch vehicle? I'll answer it. Otherwise, we should turn it over to him. Okay, well, thank you. We're happy you're all here to watch it, and got a good flight out of it.
I'm Chuck Lundquist from the University of Alabama in Huntsville, the Consortium for Materials Development in Space. Let me begin by congratulating Deke and SSI on a great flight. We got the kind of ride we wanted and are now awaiting the recovery of the payload. Obviously it came down on parachute, and we don't have a report yet from the helicopter having reached the site, so I can't tell you exactly what form the payload is in, but it came down well on parachute, so there's every reason to believe that it's a successful recovery. The recovery will be taking place probably right now. With regard to any of the specific experiments, it's too early to make any kind of a diagnosis. From the telemetry, we can tell that the timers that operated the different instruments worked, and so the 12 experiments were working one way or another, and until we look at the individual equipment when it gets back and do more detailed analysis, it's just premature to say anything about any of the experiments.
What kind of message did you receive that would make you think that it didn't go off right?
The one message or one bit of indication was a temperature measurement, but there could be other interpretations of that too. So I'd say it's premature to make any kind of a diagnosis on any of the experiments. We don't really know anything about any of them specifically. We know that the general apparatus worked within the payload. We see that on the telemetry, but just much too early to go beyond that. Any questions? Let me again say that we're just very pleased with the flight that SSI provided. It was a perfect day for it. Went very well, and we now have to analyze the results from the individual experiments to see what results we got, but I'm very optimistic that it was a very successful flight.